let's do the final part. So now I'd like to explain why the laser looks like the field looks like this bar. I think this is not a good example because probably a good example anyway. Because this bar is not so circular. For most of the higher power laser diode, the laser bar is not full circle. It's usually elliptical. And I'd like to, we will explain now how does this happen. Alright, so let's start with the simple question. Like for semiconductor lasers, it's usually in the T mode. So this question, I don't have too much time for you to think. Why the semiconductor laser is usually in T mode? In the rectangular waveguide, we usually care about the T mode. Okay, that's the mode nowadays. And the T mode can be named as following: TEMN, and the MN in the subscript. And the first number is against the order of mode in the lateral direction. And the N is the lateral mode in the vertical normal direction. So for example, TE00 means it is fundamental mode at the lateral direction and the fundamental mode in the normal direction. If it is TE10 mode, that means in the lateral direction is the first order mode. So in that rectangular waveguide, if you see from the lateral direction, it will be in its first order mode, like that. So if it's in the first order mode, there's the 0 point in the middle. So it has a node plane here. And since it's in 0 order in the vertical direction, so if you take a look from this direction, because it's fundamental mode, so it is something like this. So the optimal the field, you will see 1, 0 plane at the center or along the vertical axis, but no plane here. Alright. So you can actually, if you see a field, and you can directly tell what mode is that. For example, this is okay. So this is the TM mode. This is because this is from another paper. For semiconductor, usually we don't have. So okay, so this is a good example. This is the TE20 mode. TE20 mode, so it has second order. So it has 2 node plane in the vertical direction, and no plane in the vertical direction. So you can see by eye, tell me what's the mode, optical mode profile it is. So this is a TN20 mode, and this is the T. Okay, so let's pretend it is T. So if the electric field looks like this, then it is T01 mode. Since it has no mode at the lateral direction, no plane in the lateral direction, but 1 node plane in the vertical direction. And what is really important is the fundamental mode for some particular reason. And we will show that later. So the optical mode here, just outside or just in your sample, is called the near field. The real optical potential profile in the device. So there's some common types of edge emitting lasers, and also now we're watching along the edge of the laser. So if there's no confinement structure at all, we call it broad area. And this kind of laser actually has no lateral waveguide. The mode profile by such broad area laser is due to the carrier concentration difference That means the optical mode is strong at the center. It's not because it has a waveguide here. It's because you have a higher carrier density due to the carrier is injected from middle. So you have high carrier density, then you have a high carrier, you have a higher emission output. So you do nothing with the waveguide. So this is also called gain guided. If you see that from some paper, you will see the name called this. That means there's no intentional optical waveguide. The field intensity is actually only the gain profile due to the carrier distribution. So it's called gain guided laser. However, if you're trying to etching down some part of that, so the effect index of in the side is lower than the effect index in the middle. So you have some optical waveguide effect on the lateral cases. So in this case, it's called index guided. Laser. According to the depth of your edge, if the edge doesn't pass through the AT region, we usually just call it reach without any adjective, 就没有不加任何什么。But if we are etching through the AT region, then we usually call it deep reach. 深就比较深的，因为它吃的比较深，这是蛮直接的命法。We call it deep reach. So as also make a quiz. 来拿了我今天只剩一没有，今天除了电解那个也没来，每个人都点过一笔。OK， 好吧，那就今天放送就送到这里。你看看，如果我今天的这个 reach laser， 我如果没有把它算的话，我的 index 是7P， 那它的 index 是1，那你今天的 profile 里面只有一边是1，那你当然会解出一个 index 还是跟你旁边的这一块是相关的，所以中间的 effect index 跟旁边的 effect index 的差距是不会那么大明显。如果今天把它整个吃穿了以后，我一样做我的9宫格算的时候，我需要算这边的 effect index 吗？不需要，它的 effect index 就是7，不然或者不是7，也是某种 dielectric， 可能是 1.5、2.2， 再怎么样不是3点多。好，那横向的折射率差异自然是比较大，所以如果今天想要更好的 combined factor， 我也许会有人提出一个很暴力的建议说，我们就日语就吃穿 AT 就好了。这个就是我在上完这门课，然后呢在做我的题目提出一个建议。不过这种事情如果到业界很快被打给跳，因为你今天要制作一个雷射diode了，你要电子注入的电荷的量很高，然后呢，你既然吃穿它，那这个东西的稳定性其实是不好，因为你总是会在塞微的内。所以从理论上来讲，的确 deep range 会给你更好的 combined factor， 也许会因此让你雷射的速度变快，或者是 ratio 更低，但实际上大家不会这么做啦。你在那边抽到一点点 combined factor， 结果那个雷射的寿命减少10年，那个可能不一定是一件值得的事情。OK， 你这边执行一下。可能各种不同的 range 结构，那像这一个 bore area 这边这边两个差别在哪？这个 bore area 是真的 bore area， 什么差别都没有，你就只在上面上个电极而已。那你看这一个 bore area 呢，它会画这边叫做这个叫 HI 轻 implanted， 就是我在旁边的部分进行离子布置，就是我在边边，我先把中间需要的部分先可能用某种 harness 的把它住，然后呢开始摆进去用氢原子烘它。 那烘一烘了以后，边边的这一个地方，因为你烘了你物质的氢离子起决以后呢，它的主值就瞬间的变很高，就是看起来它不导电。所以我一个电极上去的时候，它会自然不导电的东西就形成一个电荷的 aperture， 所以载子会启动在这里。对，它是一个载子的 aperture， 不是一个光的 aperture。你把氢原子布进去了以后，对于材料的本身的电性影响很大，但是对它的折射率其实不会有什么很显著的影响。The near field means the optical wave, the mode profile in this device. But when light leading out this your laser, it will propagate. And propagate to a certain distance. The intensity of every point is the summation of the light propagation from each point. So the far field is the result of the diffraction of your near field. And what is the relation between the near field and the far field pattern? So in the near field patterns, we can, because sometimes you might, the more than the fundamental mode will recycle. So the actually near field might be a linear combination of different PE modes. So it's not necessarily only one mode, because you're rigid one, probably you can decide the second order mode or something like that. So it could be a linear combination of the different lasing modes. And the far field is usually described as the divergence angle. Because if you are talking about the real distance, surely the pattern will be larger. Put your plane further, but it has no meaning. So usually people care how the laser beam spread out and how large is the divergence angle of such laser. So the math is quite tedious. I will list the procedure, but I'm not really trying to derive it. This is really a difficult job. We only start with the schematic figure. So this is your near field. Light coming out from this small area, and probably stronger at the center, a little bit weaker in the end. So it is in the small region, it will be u of xy at a certain point times dx dy. Then this light propagating through a quite long distance and to another point at the far field. So we take the du larger x. So this is far field. So the far field of a certain point is the summation of each point at the bottom. So you need to add it up all the phases with the weight of the near field profile. Then summing up all the phases and give you the far field. And what does happen? So the duf is the small origin at the near field. Dx dy times u of xy. And it propagates with r divided, so this is the phase difference from each point. And the reason there's the r here, it is from Huygens principle, or Huygens, not Huygens, sorry, Huygens 是多少那个 Huygens Fresnel principle, Huygens 原理 so it's the result of Huygens principle. And this is the second term. Let's give you the face, right? KR give you the face. And the second term is the mathematical refinement of the Huygens principle in order to make the real result with the same total energy. So this is a mathematical refinement. So this is already what textbook says. This is also what I can tell you now. So at each point, it is from the point that you get a contribution of this term. Then you want to sum them up. So you make an integral at both sides. Alright. So we can make some reasonable approximation. The first is the cosine small theta r is the divergence angle with the specific position in the near field. But the theta large R capital R is the divergence angle to the center of your field. And because it's a far field, that means it is quite long from your laser, probably 100 wavelengths or longer. So these two terms can be approximated to be the same value. Cosine theta small r is pretty close to cosine theta large R. And second, the small r and the large r has some mathematical relation. And this is usually just geometry. Probably you can try it at home. But now we only accept that, or this class will be a geometric class. Small r is the large r minus x sine theta x. X means the position of the delta point in the near field. If you have x, y, z coordinate, and the sine axis is the sine r projecting a projection to the axis. Alright. So you have the sine theta x, that means the divergence angle in the x direction, and this is the y direction. Alright. So you can substitute these two terms back to the equation here. And then calculating every point in the near field. So it eventually goes to a term like this. So this is the turn of the electric field. This part are all constant outside. And the phase difference is the x sine theta x plus y sine theta y. Then summing in up with all points in the near field. Then the intensity is the square of the electric field. So it looks like a very long term of this one. So there's a few insight we will get from this equation. First, the total field intensity is in the reverse square of r squared. So this does nothing with the diffraction. This is true because we already put r here. So after square ratio we have r squared. So this only means we can treat the laser light as a small point source, since the detection image is very far away from the light source. So this is fine. So we can treat it. The near field might be relevant to your far field at the beginning, but with a long distance, it eventually should evolve into a severe light point light source. This is the first one. And then the second is that if you take a short look or a closer look of this equation. Okay, so we make it a bit larger here. You will write it down. The theta x should be 2 pi x over lambda, since we have a k here. And the ky is the 2 pi over lambda y, something like this. Then make some substitution to make everything in uniless, because now the x plus we let the distance to be x plus. So 2 pi x over lambda. We write the x down, or you can write it as k plus. It's okay. So it is a normalized term to its wavelength. A normalized term to its wavelength. And this expression looks just like a Fourier transform. So the far field pattern is the intensity surely is divided by R squared. This is for energy conservation. But its profile should be pretty close to its near field with Fourier transformation. Alright. So if this is the near field with the ridge laser, because the ridge is always in the level of micrometer. But your waveguide is always in the 100 nanometer or something. It is a rectangular shape of an aperture. The near field is narrower in the vertical direction, wider in the lateral direction, due to the device geometry. 就因为我们的 H 永远是几 micron 的宽度，但 AP 永远是几百 nanometer， 所以你把整个 H 的是视成一个光圈的话，它一定是一个横向发展的光圈。所以像这样的一个横向的图，经过傅里叶转换以后，就会是这样一个纵向。So the far field pattern of a originator waveguide has a longer axis along its AP direction and a narrower axis along its device or the lateral direction. Okay. So since the near field and the far field are Fourier transform pairs, if the near field is narrower at one direction, the far field will be wider in the other direction. So what should we do to make a far field pattern to be spherical? There's a few ways. Because the original wave is elliptical, so you can do with secondary optic. That means you make a lens trying to expand the direction to make it a more circular light. Then do other focusing to make it the small one you want. So that's some secondary approach. But it will need 2 additional lenses and some careful calculation. But what if our aperture is originally spherical in the beginning? So the near field is a circle. The far field will also be a circle. But this is impossible for edge emitting laser because we only AP the waveguide for a few hundred nanometers, so it's very, very difficult to make the reach only a few hundred nanometers, and it is also not healthy, very difficult to do.